Hey, welcome to The Explainer. Today, we are diving deep into the brains of modern automation, the Programmable Logic Controller, or what everyone just calls a PLC. We're going to tackle one of the absolute most fundamental skills you'll ever need, how to wire up a digital input. I mean, think about it for a second. You can press one little button, and this giant, complex factory roars to life. But how? How does that simple physical switch actually talk to the machine's brain? What's the secret language it's using? Well, that is exactly what we are going to unpack today. So first things first, let's start with the absolute basics. Before we can even think about wiring anything, you've got to understand the language a PLC speaks. And for digital inputs, it's actually an incredibly simple one. A digital input is really just a signal that has only two possible states. It's either on or it's off. That's it. You could almost think of it like a sensor just shouting to the PLC, hey, I'm here, or, well, staying completely silent. There is no in between, no kinda. It's this simple, binary, yes or no state that is the foundation for pretty much all control logic. Okay, now this is crucial. Before we go connecting wires to our PLC, we have to talk about protection. I mean, you can't have a simple wiring mistake on, say, a $2 switch completely fry the expensive brain of the whole operation, right? So how does the PLC protect itself? Well, it's got a secret weapon inside, a tiny bodyguard, and this little hero is called an optocoupler. Its entire job is to keep the super-sensitive brain of the PLC completely separate from the rough-and-tumble world of outside switches and sensors. So how does this bodyguard actually work? It's pretty brilliant, actually. When a signal, say 24 volts, arrives from your button, it doesn't get anywhere near the PLC's processor directly. Nope. Instead, all it does is light up a tiny little LED inside the input. Then, across a physical air gap, literally a gap of air, a light sensor on the other side sees that light turn on. That sensor then tells the CPU, hey, the light's on. So you get a clean, safe signal without any direct electrical connection. And that tiny air gap, that's the whole magic trick. It means a huge voltage spike or a simple wiring mistake on that $2 button can't jump across and destroy your $1,000 PLC. This idea, called electrical isolation, is absolutely fundamental to making industrial controls reliable and safe. All right, enough theory. Let's get our hands dirty, metaphorically, of course. We're going to start by wiring up the most basic component you can find, a simple push button. So take a look at this circuit. It's super simple. We've got our 24-volt positive source, right? It goes to one side of our push button. The other side of the button goes to our PLC input. Now, to make it a full circle, the PLC's common terminal is connected back to 0 volts or ground. So what happens? You press that button, you complete the path, 24 volts flows to the input, the little bodyguard LED lights up, and bam, the PLC reads an on signal. Easy as that. Okay, now this next idea is honestly where a lot of beginners get a little tangled up. But I promise you, if you stick with me, it's way simpler than it sounds. We're talking about syncing and sourcing. And you know what? It all just comes down to one simple question. Which way is the electricity flowing? Here's the key difference, right here. For a syncing input, the PLC is providing the path to ground, or 0V. So the current flows from your switch into the PLC. Got it? Now, for a sourcing input, it's the opposite. The PLC is providing the positive voltage, so the current flows out of the PLC, through your switch, and then down to ground. Let's look at a syncing setup. This should actually look pretty familiar. It's just like our first example. See how the common terminal is tied to 0 volts? So when you hit that switch, it connects the positive 24 volts to the input. And notice that arrow. The current flows into the PLC. The input is syncing the current down to ground. And here is the total opposite. This is sourcing. This time, the PLC's common terminal is connected to positive 24 volts. So to turn the input on, our switch needs to connect it to 0 volts. See the difference? The current now flows out of the PLC's input, through the switch, to ground. The PLC itself is sourcing the power. Awesome. We've got buttons figured out. But let's be real, in the industrial world, you're going to be wiring up a lot of sensors. The good news is they follow the exact same syncing and sourcing rules we just learned. The two main types you're always going to see are PNP and NPN. Now here's the dead simple way to remember it. PNP switches the positive line, so it's a sourcing device. NPN switches the negative line, which makes it a syncing device. Just think, P for positive, N for negative. It's that easy. So how do we match them up? Honestly, it's just like putting puzzle pieces together. If your PLC has a syncing input, what does it need? It needs to receive a positive signal. And who provides that? A PNP sensor, our sourcing sensor. It's a perfect match. On the flip side, if your PLC has a sourcing input, it's already providing the positive voltage, so it needs an NPN sensor to complete the circuit to the negative side. See? You always have to match a sinker with a sourcer. But what happens when your puzzle pieces don't fit? You're out on a job site, you've got the parts you've got, and they don't match. You have a sourcing sensor and a sourcing PLC input. You can't just run to the store. Don't worry, there is a super clever and super cheap workaround. Let's use that exact scenario. You've got a PNP sensor. It outputs a positive signal. But your PLC is a sourcing type, which also outputs a positive signal. They're both trying to be the source. They can't work together directly, so what do? The answer is a simple, cheap little device called a relay. So for a second, just forget about the PLC. We're going to take the output wire from our PNP sensor, that positive 24-volt signal, and we're going to use it to power the coil of the relay. That's it. When the sensor turns on, the relay's coil energizes. Okay, now what happens when that coil energizes? It closes a set of contacts inside the relay, which is really just an electrically isolated switch. So now we wired that switch to our PLC exactly like we did with our very first push button. Our sourcing PLC input gets connected to ground through the relay's contacts. We've basically used the relay as an electrical translator to fix the mismatch. It's a brilliant trick. The big takeaway here, the thing you've got to remember, is that a tiny, cheap relay can be your absolute best friend out in the field. It's a super powerful tool for making parts that shouldn't work together talk to each other. It's a fantastic trick to have up your sleeve. So, let's recap. What we've really done today is give our PLC its senses. Through these inputs, it can now see the world around it. It knows when a button is pushed, it knows when a sensor is tripped. But of course, this brings up the next big question. Now that the PLC can see, how do we teach it to think? Well, we'll tackle that next time.